who is working in the area of quantum computing on NISQ, on which application we can use in the NISQ era. So she's giving a talk on the NISQ analyzer, and we're very much looking forward to your talk.
Oh, thank you very much.
Oh, it's the wrong presentation. Okay, that's fine. It's not working. No. So, hello everyone. As I was introduced, thank you for that, Johanna. I will present you something about quantum applications in the NISQ era, and especially how we want to support the users to find a suitable quantum computer for their specific quantum circuit or algorithmic quantum circuit. And as we have heard in the previous keynotes, quantum computers will solve specific problems faster than their classical counterparts. However, they are still prone to errors and only support a small number of qubits. And these limitations determine the executable circuit size, so the width and the depth of an executable circuit. So our goal is to design such quantum circuits as resource efficient as possible. Well, now, is that working properly? Okay. Now, but there are some problems, I would say. So when we design a circuit, it's finished, the final circuit size changes in the process of compiling it and finally executing it on the target quantum computer. And therefore, several aspects have to be considered. So on the one side, we have the qubit topology of the quantum computer. So how the qubits are connected between each other. And for example, when we then map our circuit on the quantum computer, further swap gates may have to be added to enable the computation of a multi-qubit gate. And in addition, we also have to consider the implemented gate set of the quantum computer. So, for example, when we design a circuit, then several gate sets or gates are available to design our specific circuit, but later on the quantum computer, the implemented gate set is somehow reduced. So therefore, before executing it, we have to map our gates onto the gates of the quantum computer. And this also changes the circuit size, and in most of the cases it increases, for example, the depth of the compiled quantum circuit. But, this mapping on the quantum computer is done by a quantum compiler. And so besides this mapping of the gate sets as well as on the physical qubits, the quantum compiler also enables an optimization. So for example, it parallelizes the gates such that the depth of the resulting compilation result is reduced. And just using the one quantum compiler is not that easy, because already today a variety of compilers exist. And you have to keep in mind, for my specific circuit, which compiler is now the best and which compiler delivers me the most optimized compilation result. And I think the simplest case for this is just take my input circuit and use the different available quantum compilers to have then a look at the compilation results and enable a comparison between the different compilation results to then use the most optimized one. But well, simply using such a compiler is not that easy, because these quantum compilers are mostly wrapped by different SDKs. And so, for example, the Qiskit transpiler requires the Qiskit SDK to use it, or the Forest compiler, the QuillC compiler, this is the Forest SDK, and so on. And now the problem is here that these SDKs differ between each other. So, for example, these SDKs support different gate sets. So, for example, the Rigetti or the Forest SDK supports the gate sets of Rigetti, but it does not support the physical gate set of the IBQ quantum computers. So this has to be kept in mind. In addition, also the programming languages between these SDKs differ because, because I don't know, but for example, the Qiskit SDK supports programming such a quantum circuit with Python or with OpenCasm, whereas here again the example Forest supports only Python, so the Python language for Rigetti quantum computers, and Quill. And so, the circuit has to be rewritten. In addition, the other problem is that the current SDKs most only support a subset of available quantum providers and their quantum computers. So here again, for example, the Forest, with the Forest SDK, we cannot access quantum computers of IBM in this case. So now if we then really, I don't know what is this. Maybe I stand there. I hope the connection is better now. The whole problem is if we want to, for example, execute our circuit on an IBM quantum computer, but also on a Rigetti quantum computer, every time we have to rewrite our our input circuit, and this is huge manual effort. And last year we made an analysis of existing SDKs and their quantum compilers, and what we, for example, found out is that even if OpenCasm is known as the unofficial standard, there are still SDKs that do not support OpenCasm. In addition, there exist many vendor-specific SDKs, and they also, most of the cases, only support their own quantum computers, as I mentioned previously with the Rigetti quantum computer and the IBM quantum computer. However, there is the possibility that many SDKs support the modeling of custom quantum computers, so that we at least can define such a custom IBM
quantum computer, for example with the Forest SDK. However, they do not support defining target custom target gate sets. So a full modulation of such a quantum computer is not possible. And another problem is, even the formats to define such a quantum computer, such a custom quantum computers are different, such that here again we have to rewrite such a customized quantum computer. And also, this is our conclusion. The SDK has to natively support the cloud provider or the quantum computer to enable a compilation and then for sure the execution on this target quantum computer. But, there are not only these problems with the SDKs, but it also has to be considered that these quantum computers are regularly recalibrated, and this leads to changing error rates of the quantum computers. In addition, also the access to the quantum computers for making an execution of my specific circuit is hindered by the cloud providers that regulate the access on the quantum computers. So this results in waiting times. So the result is
that if we want to implement and execute our specific circuit, then we have to consider multiple quantum computers, multiple compilers, as well as their SDKs, and also the access regulations. And well, this all in mind requires a deep and versatile as well analysis, which brings us huge mental effort and huge knowledge is required for this. And so our approach is here the NISQ analyzer, as you may know. So we have our user with its specific input circuit, and the first step is we translate this input circuit into the required formats of the supported compilers. So for example, if we have a Quill implementation, so for Forest SDK, then it is translated into OpenQASM. If the user wants to compile it on IBM quantum computers, then we use, for example, here the Qiskit transpiler, and then it has to be translated into OpenQASM. Another example that we also support is the Tcad compiler. So here, in this case, it also does not support Quill, so it has to be translated into PyQuil. And then, in the next step, we compile these translated circuits on each available quantum computers that we have. So in this case, we use our provenance system QProv, as Benjamin already introduced in the previous keynote. And here, we take each available quantum computer and compile it on with every quantum compiler, and that's it. And so finally, we have then several compilation results for a specific input circuit. So now, what we then do is we analyze the compilation results based on several metrics, but I will come in detail to them in my paper presentation later on. But what we also do is we estimate the executability of the compilation results. And therefore, we take the average decoherence time and divide it by the maximum gate time of the specific target quantum computer. And this is then an estimate about how the maximum depth should look like. And this has to be then greater or equal than the depth of the specific compilation result. So then, as a result, we just have a list of compilation results that should be executable on the quantum computer. So with not too much errors. And now let's have a look at this list. So for example, here we have then the compilation results for different quantum computers made with different compilers, in this case with the Tcad compiler and the Qiskit compiler. And what we, for example, can see here is when we have a look at the IBM Lima quantum computer, then we can see, for example, that regarding the total number of operations, here the Qiskit compiler or transpiler requires 62 number or gates, whereas, for example, then the Qiskit requires 62, and the PyTcad compiler requires only 45 operations, or this compilation result requires only 45 gates. So here again, we have to consider multiple compilers to then have our optimal or most optimal compilation result. But now with this list, the question arises, what should the user now select to execute it on the target quantum computer? And therefore, we enable the prioritization of this list of compilation results, and therefore we use different methods, but I also will come to this later in my paper presentation. And so finally the user has a ranking of compilation results and then can select one of them. And then the final step is to execute it on the target quantum computer. So that's the approach of our NISQ analyzer currently. And
now I want to show you some prototypical implementation screenshots. So what we can here see is the open source variant of the Blank platform. So here the focus is especially on our prototypical implementations for our dissertations. And yeah, here we can see a list of different algorithms. And now, for example, let's have a look at the Grover algorithm. And yeah, this algorithm also has an implementation. So it solves the satisfiability problem. And now we want to use it with the NISQ analyzer. So what is the right quantum computer to execute it on? And therefore we can start a new analysis. And what we there have to specify, so we enable the user to select all the vendor of the suitable vendor. And then he or she has to add the specific token for this cloud provider. And finally, the user can also select between different compilers that are able to compile on the target quantum computers, or just one of them, for example. And there's also the possibility to select if also simulators have to be included. So now then this analysis takes some time, but for example, if it was a Quill implementation, then the first step is to execute it on the target quantum computer with the different compilers. Now is to translate this implementation into the required formats, because as the Qiskit transpiler as well as the PyTicket compiler do not support Quill. And therefore it's on one hand translated into PyQuil, for example, or in OpenChasm to then enable the execution, or first the compilation on the target quantum computer. But well, this compilation then requires some time, as we first have to translate it, then we have to compile it on, or with every quantum compiler we support on every quantum computer. But finally, we have then this list of compilation results, as I presented earlier. And what we also do in the background, what we can here see, for example, is we also check if the QPU data changed in the meanwhile, so if there was a recalibration of the quantum computer. And well, here we can see again the different compilation results for the different machines as well as the different quantum compilers. And yeah, now we can also click on prioritize, and yeah, now the user is able to select either between predefined preferences, so for example a fast and a precise execution result, or the user can still define their own individual weights based on giving points to each metric to define then a weight for them. And well, this also takes a short time because we use specific optimizers, but it's also then part of my paper presentation. And then, then at the end we will have a ranking of this compilation results. And what you here can see, for example, the simulators are as expected at the first places because they do not have any error rates and so on. And therefore, after the sixth place, we have then the real quantum computers. And here, for example, you can see also, in the meanwhile, the recalibration occurred, so then it is recommended to analyze again. And now we can also, with the different metrics, have a look at how the error rates change and so on. And the last step is then also to execute it on the target quantum computer. And so here, after the result returned to the user, we have here the count number as well as the histogram intersection value. So we, in parallel, execute the circuit on the simulator, and then we use histogram intersection. So we overlap the histograms of the simulator over the execution results of the quantum computer. And so we have a quality measure of how good this execution result was. Yeah, and then, so this is the chain of the NISQ analyzer, but there is one more thing. Yeah, so let's assume, so first go a step back. Let's assume we have a user that just wanted to factorize a specific number, but don't want to implement it by itself or herself, and then there exists already a few implementations, so at least the user knows, okay, I require SURE for this execution or a calculation, and then, well, the user now have this mass of implementations, and the question is, okay, which implementation is the best to calculate my specific input value? And yeah, this requires manual effort, as well as then this approach of finding the quantum computer with enough qubits, which we solve with our NISQ analyzer. But yeah, it still requires immense effort and knowledge to select a suitable implementation for my specific input value, if I don't want to have the knowledge to implement it by my own, or want to avoid this effort. And therefore, our additional approach of the NISQ analyzer is, yeah, we have the user, and the user can now select out of a repository the suitable quantum algorithm, and then the user can also, the user defines what is the input value they want to compute. And as a first step, yeah, we have a set of implementations for this specific algorithm, and in the first step, the NISQ analyzer then compares the input value with the selection rules attached to this implementation. So the programmer of this implementation defines a selection rule. So for example, the implementation has input range of 0 to 1024, and now what the NISQ analyzer does is, yeah, it inserts our 255 and checks, okay, if this implementation can calculate the specific input value or not. And the implementations that are able to calculate this are then handed over to the quantum computer selection, what we've also seen in the previous slides. So here again, we compile them and then check the executability and so on, and can also later enable the execution of the implementation. So here are also some screenshots of this approach. Here we are in the context of a specific algorithm, so not in the deeper context of a specific implementation. And now when we want to start this analysis, the user first has to define the input value. So for example, this 255 if it's for SURE. And then also define the cloud service that we provide, and also insert the token for the compilation and later execution. And what we then got is, yeah, not only the compilation results of one input circuit, but for all of the input circuits that can execute or calculate the specific input value. And in the future, we also want to support there the prioritization of the compilation results. So what's the conclusion? What we've seen is that selecting or even designing and executing a specific input circuit, yeah, there's really deep knowledge needed and also a manual effort, and it also requires to consider the different quantum computers, compilers and SDKs, but also the access regulations of the providers. Furthermore, yeah, when we want to, for example, have especially precise or fast execution results. But what we here presented you is an approach that enables us the automated selection, translation, compilation, prioritization, and finally the execution on the target machine. And it's a plugin based system, so further attributes, SDKs, metrics, and so on can be added. So what we want to do in the future is we want to add further SDKs, and we also want to enable a deeper analysis regarding the estimation of when is a specific circuit executable on the target machine. And yeah, we also want to integrate it into QHANA. Thank you for your attention.
So of course we want to open the audience for questions. Are there some questions to talk? No, it's really hard to hear the questions in front.
Hi, thank you for the nice talk, first of all. So when designing basically the input circuit, that is still something that should be done manually, or are there also tools that help someone do that?
So supported from our side or in general?
In general.
Yeah, I think there are already some tools where you can click and select, something like that. But in our approach, yeah, either we have this assumption that we have already a set of implementations where the user can select, or where it's automatically selected, or the user comes with their specific implementation that was already implemented.
Okay. And I think I didn't understand how you get basically the scoreboard. So the score, the intermediate results basically, where you list basically how good each implementation would be. Is it so until that point you didn't execute anything on the quantum computers, right?
Exactly.
So it is based on a simulation or previous knowledge, or how do you get these results?
So regarding the ranking, or
Yeah.
still, okay, yeah, that I will present in my paper, but yeah, it's about, we look at the previous input circuits that were executed and compiled. So we use prior data.
Yeah, that's some kind of data. Okay, thank you very much.
Thank you.
So you have to come back in the next session where all the details are then provided. Any other questions?
So this seems quite computationally expensive, right? If you're compiling it with all the different compilers and simulating. So is this an interactive process, or is it something that you kick off and then you look at the results the day after?
So in interactive, in the assumption that the user can have a look at it or previously selected before it is then compiled and executed.
Here's my circuit, I hit the button. How
Yes.
long am I waiting until I get to see the table?
And that was the only interaction. So currently it's just I compile on every quantum computer that's available. But such pre-filtering, I would say, is future work. So that, for example, not the user is saying, okay, just kick this out or something like that, but that we are able to estimate, okay, this quantum computer will definitely not deliver us good results, so that we also skip the compilation on this quantum computer.
Okay, but how long does it take from here's my circuit, and now I get to see the overview? Because my experience is that if you're not happy with the results, you go back redesigning the circuit, right? You try to find to lose 1 or 2 qubits, and then you try it again. So I wonder how interactive you can make it.
So this process of clicking analyze and then getting the results, I think it's about 3 minutes. But as I mentioned, so we want to add this pre-filtering to, for example, reduce also this compilation process. But yeah, user interaction, currently there is not a step that the user can have more insights where, in case or when it's currently compiling, but yeah, it could be also an opportunity. Thank you.
So we have time for one more question, if there is any. other ways we would go. Thank you, Marie. Marie again, thank you very much.
Thank you.
And then we would get to the last talk of this session for today. It's the second industry talk we have now. I have the pleasure to introduce Stefan Werner, who is coming from IBM Quantum from Zurich to us to give us a talk.